So let's talk about immunizations and immune testing, vaccines. And I know this is a controversial um, subject for some people, but it's important that you understand what these things are and what it can cause and what it doesn't cause. So, first of all, um, going way, way, way back, Chinese noticed that children who recover from smallpox, which is, pandemics most of the time, didn't contract the disease again. So they infected young children with the material from the smallpox scab to induce immunity in these children. The problem with this is it's called variolation, and it was used in England and America, but it was stopped because you were infecting these children with the actual smallpox. So you could easily die from this, okay? Because they didn't kill the virus, they just gave the smallpox to these kids. In the late 1700s, Edward Jenner discovered the process of vaccination. What happened was he noticed that the milkmaids would get this cowpox, very similar to smallpox, and they noticed that these milkmaids didn't come down with smallpox. So he started inoculating material from somebody that has been infected with cowpox and basically vaccinated his family. Brave enough. And they didn't develop smallpox. The first vaccine came by Louis Pasteur, and a vaccine against Pasteurella. And basically, the practice of transferring these antibodies was developed when it was discovered that vaccines protected through antibody. Okay. Now, depends on where you are. There may be social, economic, and political problems that may prevent many developing countries from receiving vaccines. But we've been pretty good with smallpox and polio and that sort of thing. There are some pathogens that we have not made effective vaccines for. We're working on it. The mRNA vaccines is the future, some of them. Vaccine-associated risks that have been in the public, it may discourage people from taking the vaccine. It can discourage investment in developing new vaccines. But if you think about it, we'll look at it, and you're going to get a vaccine assignment prior to these vaccines really coming into use. I will tell you, kids got sick all the time. I grew up before most of these vaccines were developed, and we'll talk about that. So the children caught every childhood illness that we had, every summer. You would keep your fingers crossed that you wouldn't get polio or something like that. So, we have really come a long ways, and it is because of vaccinations. So there are two ways of getting immunity. It is active immunity, active immunization, administration of the vaccine so that the patient actively mounts an immune response. Okay, they have to form the antibodies. Passive immunity, we've kind of talked about this. Basically, we give them the antibody. This is basically a chemoglobuline shot. All right, we're giving you the antibody. It is very temporary to get you through the infection or get you through what may be an outbreak, but it doesn't connote long-term immunity. Active immunization does. So there's a difference between a vaccination and an immunization. A vaccination is the process of administering that vaccine, so you get a vaccination. Immunization is your development of that response. Okay. Passive immunity, as I said, you are given an antiserum. It preform antibodies, usually an immunoglobulin shot or convalescent plasma from somebody that's recovered. A lot of times, these are made from horses. Used to be. It's used to provide immediate protection, a recent infection, ongoing outbreak to protect you against something that's occurring. There are issues with these passive immunities. Again, they can contain antibodies against antigens, other antigens that not the one you're looking for. It can trigger allergic reactions. It can be contaminated with viral pathogens, depending upon, where they got this antisera. And again, the antibodies degrade quickly. It's only a short-term fix. Okay. So one of these is human immunoglobulin, IG. It's pooled plasma from the blood bank pools it from thousands of healthy donors. And it provides a baseline antibody protection. So you can get it IV. It's often used for patients with immunodeficiencies to replace missing antibodies or as an anti-inflammatory. You can give it intramuscularly, and it's frequently used for post-exposure prophylaxis. Again, like measles or hepatitis A, when you have an unknown or incomplete vaccination history, and you can do those kinds of things. There are hyperimmune globulins. These are specialty globulins to be harvested from donors who have high concentrations of the antibody against a specific disease. Either they've recently recovered or they've had targeted vaccination, and you can see the list. Rabies, hepatitis B, tetanus, varicella zoster, and cytomegalovirus. Okay. I've seen them give cytomegalovirus vaccine to stem cell transplant patients. 85% of the population is CMV positive, but if you are CMV negative, you must receive everything you receive, every blood product and everything you receive must be CMV negative, or you're going to develop it and you're already immunosuppressed. So not a problem, but you can see these vaccines are used to treat active tetanus or high-risk individuals pregnant for chickenpox. Hepatitis B, this is the one to protect the newborns against HIV, not HIV, hepatitis B positive mothers. And they usually get, because sometimes this may not be positive at the time the mother is delivering. It's always, and this will do these babies' livers in bad. All right, so antitoxins and antivenoms, these are typically developed by immunizing animals, often a horse, with the toxin or the venom, botulism toxin, neurotoxin. They said that, to neutralize that. Yeah. Diphtheria antitoxin, and we don't see that too much. And then our venoms, antivenoms, we milk these snakes and develop antivenoms. Okay. All right, monoclonal antibodies. This is a very highly specific antibody that's engineered to an exact target. There are some that we use particularly. One is against the RSV, the respiratory syncytial virus. This is given to high-risk infants. This is severe. We'll talk about respiratory syncytial virus when we get to the respiratory system. But it's a severe lower respiratory tract disease, and it's really bad in kids. I've seen many a kid hospitalized because of RSV. And we do have these monoclonal antibodies that can be given to prevent severe infection. There is a different one that is widely used for the prevention of RSV. And then our lovely little COVID. It is a monoclonal antibody. And it was authorized for COVID-19 or early treatment. And so these monoclonal antibodies are, again, they can be given to help through those early stages of the disease, and hopefully you don't have a major complication. These are antibodies that are given, again, so they're not going to last very long. They're just going to get you through that immediate issue. Okay, those are passive. Now let's look at the active ones. Again, these we get, and we have to develop our own antibodies. So when you get through the series, a lot of these, depending upon what they are, will connote lifetime immunity, as long as your immune system is functional. Okay, some of them you'll have to get recurring vaccinations like tetanus, but they do very well. So the scientists decide which type of vaccine they will make based on several factors. There are several different vaccines: killed vaccines, live attenuated vaccines, mRNA vaccines, these conjugate vaccines, toxoid vaccines, and viral vector vaccines. Let's kind of go through these. Inactivated. It means that basically the vaccine contains either the whole bacteria or viruses that have been killed or altered so they cannot replicate. Okay? They do not contain any live pathogen. They cannot cause the disease against what they protect, even in people in severe weakened immune systems. However, they don't always create a strong or long-lasting response because they are attenuated. They have been altered. One of the things I can show you is or talk about before most of these vaccines came out. And again, I came down with a whole bunch of these diseases. When I was working in the lab, I used to test for these, and we would test people for immunity, especially for those people that were coming in and hospital workers. You want these hospital workers to be immune. And one of the things that was required is, as you were coming in as an employee, you had to have certain levels tested to make sure you were immune. And if you weren't, then you had to start a vaccine series. When I did that, one of the interesting things is that one I did, and it's not on this list, we'll talk about German measles, rubella. And I had German measles. And so when I tested the majority of the employees coming in, their level of immunity, there's a way we measure it, it's just amount we'll talk about, was right over the limit of where, yes, I'm immune, but I don't have much over. Okay, let me just make this up. Let's say in order to be immune, you had to have 2,000 units, a value of 2,000. Most of these people sat around 2,400. Mine, because I had German measles, was 5,500. And this was, 40 years after I'd had German measles. Okay, so there is a difference between getting the disease and getting the vaccine. But the whole thing with the vaccine is you want to get a level of antibody up high enough that you will be immune. without getting that disease. So these hold kill vaccines, you can see there's a shot, polio shot, usually give it by mouth now, a hepatitis A vaccine, rabies vaccine, flu, anthrax, and meningococcal. Attenuated vaccines, attenuated live vaccines that we use in a weakened or attenuated form. These vaccines are so similar to the natural infection, they help prevent it. They create a long-lasting immune response, usually 1 or 2 doses for most of these vaccines. Think of shingles, can give you a lifetime protection against the germ or the disease. There are some limitations with these live attenuated ones. They do contain a small amount of weakened live virus. And so some people should talk to their healthcare provider before receiving them because if they have a weakened immune system, long-term chronic issues, and people who've had organ transplant. It's not a good one. These guys need to be kept cool so they travel well. That means they cannot be used in countries with limited access to refrigerators. Live attenuated vaccines, your MMR, your rotavirus, smallpox, chickenpox, yellow fever. I'm just giving you an examples of these. Your mRNA vaccine really became famous during the COVID outbreak. These use messenger RNA instead of a lipid membrane, and this fatty cover protects the messenger RNA when it enters the body. Once it gets inside, the machinery inside the cell translates it into a protein, and this typically lasts a few days, but in that time, sufficient antigen is made to stimulate an immune response. Then it's broken down naturally and removed from the body. They are not capable of combining with our genetic code. They do have several benefits. It's a shorter manufacturing time. They don't contain a live virus. There is no risk of causing disease because what we've done is manufactured that sequence. Okay, example of it is COVID-19. The new one is DNA vaccines they're working on. It is a type of vaccine that transfects a special antigen coding DNA sequence into the cells. The cells produce the antigen, and that causes an immune response. They theoretically have advantages over conventional vaccines. They have ability to induce a wider range of responses. Several of these vaccines have been tested in veterinary use, and in some cases, protection from the disease in animals have been obtained, some not. This may be the way of the future. But again, we're working in our mRNAs. We're moving to now possibly the DNA vaccines, but that's the wave of the future. Another vaccine that we can use is subunit recombinant polysaccharide and conjugate vaccines. Okay. These use specific pieces of the organism. It's protein, it's sugar, it's capsid, okay? They typically contain 1 or more specific antigens from the surface of that pathogen, and you don't have to use the whole pathogen. The immune response can focus on that small number of antigens. It's, you only use, again, specific pieces. They give a very strong immune response. They can be used on almost anybody, including people with weakened immune systems and chronic problems. One of the limitations is you do need booster shots to keep an ongoing protection against these diseases. Some of these examples, and you can see that we've got a couple different types of hepatitis B vaccines. So, yeah. So, you can see that list. We have some pretty good ones that are going. They did change the pertussis because they had problems with it, and this is the new one that they've added. Recombinant vaccines Um, they use bacterial yeast cells to manufacture the vaccine, and they take a small piece of that DNA, or the bacteria we want to protect against, and we insert it in manufacturing cells. And I gave you an example to make hepatitis B, take part of the DNA from the hepatitis B virus, insert it in the DNA of a yeast cell, and then the yeast cells are able to produce one of the surface proteins, and then that is purified, and we can use it as vaccine. Toxoids, you got to get a hold of that toxin. What they do is, what you're doing is you're creating an immunity to the part of the germ that causes the disease instead of the germ itself. Okay, the immune response is targeted to the toxin, like the tetanus toxin, the diphtheria toxin. Botox, I just want to mention, is not a vaccine. It is made from botulinum, but and they're injecting it in tiny, tiny, tiny amounts, but you get too much and you can really have some problems with it because it is, made from botulinum, so botulism. But we do have a vaccine against these toxins. Viral vector vaccines use a modified virus, which is the vector, and it is delivered with these instructions and a code, a genetic code, into human cells. And once inside your cells, use these instructions to build virus antigen. And it teaches your immune system to recognize and fight off the actual disease. Some of these different viruses have been used. Influenza, measles, adenovirus causes the common cold. Adenovirus is one of the viral vectors used in some of the COVID-19 vaccines that were studied in clinical trials. So this is another kind of wave of the future that we're looking at. All right. Now we get into vaccine safety. There can be problems with an immunization. Most of them are very mild. Pain at the injection site, blaze fever, particularly with COVID, a lot of them, and very, very rarely seizures. You can always get a risk of anaphylactic shock. That's why you always have to stick around for a little while. And you don't get the attenuated viruses don't give you the long lasting that you want. There have been allegations that certain vaccines cause or trigger autism, diabetes, asthma. I can tell you, if you look at the studies, the studies have been done over and over and over again with large amounts of people. The research does not substantiate these allegations. We cannot find a link between these diseases and these vaccines. Okay. I will tell you, when we started the vaccines in the 1960s, we didn't see this. And they've done plenty and plenty of studies. All right, how do they produce a vaccine? You can see this. You take that gene, that virulence, you take a virulent pathogen with antigens, the virulence gene is deleted, and the harmless little pathogen is then used. Okay. And you can go through these, and there are different ways of inserting these, and I'm not going to go crazy with these, but these are kind of the different ways that you can make a vaccine. Okay. You can insert it into a virus, you can insert it into a yeast cell, you can insert it into a plasmid vector, and this is again some of the ones that we were talking about. All right. There is a vaccine schedule. This has been updated. This is the updated one based on the CDC. It is obviously different because we have new Secretary of Health and Human Services. but this is the official one. If you go to the CDC, that will be the official one. Usually what they did, I know there's been controversy about hepatitis and some of these schedules and why do we get so many vaccines. What they're trying to do is protect the baby, protect the child. Okay. Again, with the hepatitis, there was a discussion on the hepatitis, but you don't know if the mother has hepatitis. And she may have caught hepatitis during the pregnancy, and her hepatitis antigen is not high enough to detect. And she's actually given that hepatitis to the baby, and that baby get the hepatitis B, and that baby has a major issue with liver problems and for the rest of its life. So what we're looking at with these vaccines is trying to protect kids and trying to keep these children from getting as many of these childhood diseases as we got in our lifetimes. Some of these, people talk, well, the kids should get the diseases. Well, that's okay, but I'll tell you that way back, when I was a kid, kids died. Kids die from this. I'm going to show you. These infections can be bad, and kids can die. I know that I have visited cemeteries. My parents are buried, and there's a section in the early 50s, and I researched that, where it's just kid after kid after kid after kid died. And they died from polio. Okay? And, we now vaccinate against that. Children have died from, polio. Kids can die from polio. I had a cousin get polio. He was in basically braces in his legs for his young life. He is now in his 70s, and he is developing the complications that come from having polio. After you get 50, the virus is still in your cells, and it starts to weaken the muscles. And he is now having serious issues, and they're all because of the polio. So you think about, not wanting to vaccinate, but you have to think about the long-term effects. Again, rubella, German measles. Well, I don't want, why can't they just get German measles? Well, here's the problem. If you get German measles, somebody gets German measles, they may not be symptomatic yet. They come in contact with a woman that is in her first trimester of pregnancy, and that woman gets exposed, and that baby will have some massive defects. So you have to think about it. You need to study these diseases and make a concerted, logical decision of, do you want to vaccinate or not? And that's going to be part of the assignment we're going to take a look at. So when you do get vaccinated, this is your response. All right. If you get a passive immunotherapy, as I mentioned, you get the injection, you get a high level of antibody, and then it drops off very quickly over time. When you get an active immunization, you get that initial injection. It takes a little while for the immunity to get there. Then you get a booster, it goes more. Then you get a booster, you go more, and you finally get up to this active level of IgG, and it's going to stay that way. It may be long term, or you may have to come back and get a booster, like with tetanus or so on. So I put in here the effectiveness of vaccines so that you can see what is going on. Here's 1950, the introduction of the Salk and Sabin polio vaccines. You can see per year cases, 40,000 cases of polio a year, usually in the summer. And they introduced the vaccines, and boom, we don't have polio. Measles. You can see it. Look at the number of thousands. This is a very contagious disease. It is the most contagious of the childhood diseases. 700,000 kids in 1960. Okay? They introduced the vaccine. People started vaccinating. And look at this. And now we're starting to bump up again because people have stopped taking the vaccines. And you can see the same with rubella. High cases, 50,000. Just German measles, not a fun. I mean, it can affect your eyesight, your hearing. A lot of kids lost their hearing. It damaged their eyesight. We're down to like none. And again, the same thing with mumps. Boom. Okay. So these diseases do have serious complications and can have them. So, potential for eradication of disease, the factors, can you eradicate these guys? Like we basically have done with smallpox. First of all, you need the ease of the diagnosis and the treatment. Low prevalence of subclinical diseases. You get the disease, you don't have a subclinical disease. There is a high disease burden and an economic impact, and immunity is long-term or lifelong. The disease cannot be reactivated, and the disease has a predictable seasonality, like polio. I mean, this is perfect. This is a perfect example. Things that are associated with that agent is lack of an animal reservoir or vector, only one causative agent, and a short incubation period. Okay. So what we get with vaccines is it can confer a long-term protection in just a few injections. Most of them have minimal handling and storage, simple administration. They can be administered with other vaccines or adapted to childhood vaccination schedules, and they have very few side effects. That's what you want with a vaccine, and that's how you eradicate a disease. All right, like smallpox. You use these things. This is what you want to do. Okay. And again, herd immunity, we talked about this before. What we want to do is get the population above that level for herd immunity. Okay. So if herd immunity for measles is 95% of the population has to be vaccinated, that remaining 5% will be protected because that will not be spread. Okay. And we've already gone through that in that other lecture that I did. So what I want you to do is go and look at the vaccine assignment that I've assigned, and you're going to research a vaccine. And there are several questions you have to answer. And there's the information of how to submit it. And we're going to make it as basically a case study. So you're going to submit it, and it's going to be a discussion, and you guys can start to talk about these different vaccines. But you guys are healthcare professionals or healthcare wannabe professionals, and you need to be aware of this because you guys are going to get the questions. So I want to make sure that you understand this, and make sure that you can at least talk somewhat intelligently about these vaccinations. And I think it's a real important assignment. I've done it many times in the past, and the students are amazed with some of these vaccinations. Okay, so hopefully you will enjoy the assignment.